Our day-to-day life depends on electrical energy. Currently, our energy needs are mostly fulfilled by conventional energy sources and they are limited and depleting. Therefore, we need models and mechanisms to utilize renewable energy sources efficiently. Renewable energy sources such as solar, wind, biomass, or biogas are clean, emission-free, and abundantly available in nature. Recently, in this direction, a smart energy community models are proposed. In the smart energy community, members of a geographical location make a cooperative group with the aim to take care of the energy needs of their community. Hello everyone, I'm Syed Iqbal Alam. I'm a postdoctoral fellow at the Technology, Management and Entrepreneurship Center, University of New Brunswick, Canada. I'll present our work on regulating the number of prosumers and consumers in a smart energy community. This is a joint work with Dhiren Shukla. We published this work at 2022 IEEE International Smart Cities Conference, which was held in Cyprus in September 2022. You can find the details in the description below. In this presentation, we'll introduce the problem, then we'll see why we use the smart energy communities and how it will help us in uh, making a community self-sustainable. And then we'll go through the problem formulation and we'll see the regulation problem formulated as a distributed constant optimization problem. Then we'll have a look at the solution approaches. Then finally, we'll go over the experimental results and we can find that following the solution approach, the community members can achieve the optimal values and the community can achieve social optimal value. Smart energy communities, as I said earlier, in the smart energy communities, members of a particular geographical location, they come together to make a cooperative group with the aim that they achieve a social optimal value and they can achieve a common goal. A smart energy community utilizes the existing local infrastructure and it enables the community members to participate, coordinate, and cooperate for the welfare of the community. It also facilitates balancing the members' needs and preferences, and the members can obtain some monetary benefit. However, one of the technological challenges is to develop mechanisms to handle the uncertainty in energy production and consumption patterns. As we know that the renewable energy sources production depends on the weather conditions and other factors. So handling those and developing mechanisms to handle the uncertainty in this production is a challenging and interesting problem. The smart energy communities can help us in becoming an energy self-sustainable community. It also can help in achieving a cleaner and more affordable energy. Smart energy communities can facilitate social interactions. The community members can interact with each other. All these facilities are not available in the traditional energy systems. So as I said earlier, our solution is to regulate the number of prosumers and consumers in a smart energy community. So what is a prosumer? Basically, prosumer is a consumer which can also produce energy. For example, in this case, you can say that a household has solar panel installed and the wind turbines. And they are also connected to the power grid. So they can take energy from power grids and they can produce energy also through their solar panels and wind turbines. And if they produce more, then they can sell it to the power grids. Now suppose a scenario in which the community has households and each household has either solar panel installed or wind turbine installed. So we will consider the case of heterogeneous energy sources, and the community can sell the surplus energy. If they produce more energy, then they can sell it to other community members or outside the community to gain some monetary benefit. The members can support especially able people also, and they can also support in uh, reducing the energy poverty, and it can help in the community or the environment to become self-sustainable. They can also have an impact on the prosperity of the society and can help in achieving the net zero emission targets. Our basic model is that we consider a central server which keeps track of the active number of consumers and prosumers. So in this case, we consider that there are a set of consumers in the community and there are a set of prosumers, wind prosumers and solar prosumers. They do not interact with each other. However, they send whether they are active or not to the central server, which keeps track of those. The notation, we use N for solar prosumers, M for wind prosumers, and U for energy consumers. Index I denotes is for the solar prosumers, J for wind prosumers, and U for energy consumers. Psi ik, it is in 0 to 1. When the prosumer I is active or it participates, produces energy, then psi ik will be 1, otherwise psi ik will be 0. Similarly, eta jk is in 0, 1 and denotes whether the wind prosumer produces energy at a time step k or no. And similarly, zuk is also in 0, 1 and it denotes whether consumer u participates, consume energy at a time step k or no. If zuk equal to 1, that means it consumes energy at time step k, and if it is 0, that means it does not consume energy. Xik denotes the average of the number of times solar energy Gi was produced in energy was active until time step k. Similarly, Yjk, which will be in 0, 1, it denotes that average number of times wind prosumer J was active until time step k, where J is the index for the wind prosumers, J equal to 1 to m. Zuk is in 0, 1 and denotes the average number of times consumer U was active until time step k, where U is 1 to U. To capture the costs, we consider the cost function. For the prosumers with solar panels, we denote Fi, denotes the cost function of prosumer with solar panels, and it is mapped from 0, 1 to R plus. Similarly, the cost of the prosumer J with wind turbines is Gj, which is mapped from 0, 1 to R plus, and Hu denotes the cost function for the consumer, which is mapped from 0, 1 to R plus. Notice that the cost functions are convex, continuously differentiable, and increasing. This is our assumption on the cost functions. Now, a regulation problem can be formulated at the following optimization problem. We denote x as the vector x1 to xn, vector y as y1 to yn, and z as z1 to zu. And we minimize the total cost over the community. It is for the cost for solar panels. Solar prosumers is Fi xi, which is summed over I equal to 1 to m. Similarly, j equal to 1 to m. Gj yj is the total cost for the wind prosumers, and u sum over u equal to 1 to u. Hu zu is the cost for the consumers. These are subject to the capacity constraints. So the sum over I equal to 1 to n xi equal to cs, the capacity, desired capacity of solar panels, and j equal to sum over j equal to 1 to m yj is the total number of desired wind turbines CW, and it should be equal to u equal to 1 to u sum over u equal to 1 to u zu is equal to sum over I equal to 1 to n xi plus sum over j equal to 1 to m yj, and xi yj's zus are greater equal to zeros. We developed algorithms that calculate the number of prosumers and consumers in the smart energy community. And as we saw, we considered the heterogeneous energy sources such as solar panels and wind turbines combined. In our solution, the prosumers and consumers, they do not need to share any information with other users or prosumers or consumers. They also do not share in cost function or averages with the central server. They make their decisions based on the probabilistic rule, and they aim to achieve the optimal values over long-term averages as mentioned in this equation. So here we denote that limit k tends to infinity xik equal to xi star, where xi star is the optimal value, and we define the averages as xik. Similarly, we can write for yj and yjk and zuk. Now, as the central server, it keeps track of the average. It keeps track of the active number of prosumers and consumers, and it sends the feedback signals to the community members. So for the feedback signal for the prosumers with solar panels is denoted by theta s k plus 1, which is equal to theta s k minus tau s by k plus 1, sum I equal to 1 over sum of I equal to 1 to n psi ik minus cs. So here notice that tau s is the step size, which is in 0, 1, and it is decreasing over time. So tau s is constant, but tau s by k plus 1 is decreasing over time. So such type of equations can be seen in stochastic approximations and adaptive control. After receiving this feedback signal, the prosumer I responds with probability phi is xik to decide whether it should be active at the next step or no. So phi is k, it is defined as theta sk, the feedback signal, times the average allocation xik by the derivative of the cost function fi. Similarly, we can calculate the feedback signal theta wk plus 1, which is calculated by the central server and sent to the community. And after receiving this feedback signal, the prosumers with wind turbines, they calculate their probability and decide whether they should be active or participate at the next time step or no. And these equations are similar to the theta w is similar to theta s k plus 1, and phi jw is similar to this to phi is. So basically, theta wk plus 1 is theta wk minus tau w, which is a constant again in 0, 1 by k over k plus 1, and it is summed over j equal to 1 to m eta ju is jk minus cw, and the probability is calculated as theta wk yjk by gj dash yjk. And for the consumers in the community, the feedback signal is calculated as follows, and basically it is how many consumers are active at the time of step k minus the active total number of active prosumers. And here again tau c denotes the constant which is in 0, 1. And after receiving this feedback signal, the consumer U responds with the probability phi UC, which is again depends on the theta c k and the average allocation ZU by the derivative of the cost function HU. So it works like that. Once the prosumers and consumers join the community, they obtain some parameters from the central server, and the central server knows how many number of prosumers and consumers should be. Means what is the desired number of prosumers and consumers to be active at a time. And then it calculates the feedback signals and sends this to the community. And after receiving the feedback signals, the prosumers and consumers calculate their probability and decide. They calculate the Bernoulli values also, whether they should be active or no based on their probability values. For the experimental results, we set up the following experiment and we choose the following parameters. We choose n equal to 100 prosumers with solar panels, m equal to 80 prosumers with wind turbines, and u equal to 160 consumers. We choose capacity Cs equal to 50 and Cw equal to 60. We choose the cost function as chosen by Morat and Pinson in reference 9. For solar energy prosumers, we choose a phi xi equal to a1i xi plus b1i xi square. Similarly, for wind energy prosumers, we choose gj yj equal to a2j yj plus b2j yj square. For energy consumers, we choose hu zu equal to a3u zu plus b3u zu square for where u goes from 1 to u. Here notice that to create different cost functions, we use a1i, b1i, a2j, b2j, a3u, b3u, which are random variables. And in our experiment, we choose the uniformly distributed random variables. We obtain the following results. This figure shows that the full evolution of average number of times prosumers with solar panels were active, and the average number of times prosumers with wind turbines were active, and the evolution of average number of times consumers were active. We can observe that this average number of times prosumers with solar panels that were active, it converges. And similarly, in figure B, we can see that the average number of times prosumers with wind turbines, also the average values also converge over time. Similarly, in figure C, the evolution of average number of times consumers that were active, it also converge over time. This figure shows the histogram of the absolute difference of average number of active solar prosumers and the optimal values. Similarly, B shows the histogram of absolute difference of average number of active wind prosumers and the optimal values. And figure C shows the histogram of absolute difference of average number of active consumers and the optimal values. Here notice that we plotted these values at the last time step. And we observed that in all these figures, A, B, C, we observed that most of the values, the absolute difference of average number of active solar prosumers and the optimal values, and the absolute difference of average of active wind prosumers and its optimal value, and the absolute difference of average of average number of active consumers and its optimal values, they lie below 0.05. So the difference is the absolute difference between the average values obtained by our solution approach and the optimal value. It is less than 0.5. So they are basically quite close to each other. So one more thing I would like to say here is that the optimal values are calculated using CVX, and they are done in a centralized way. So we formulated the problem for a centralized solver. So the optimal values are obtained by the solvers. In this figure, the evolution of total number of active prosumers with solar panels are plotted in figure A, and figure B shows the evolution of total number of active prosumers with wind turbines, and figure C shows the evolution of total number of active energy consumers. So we can observe that in figure A, these values, the total number of active prosumers with solar panels, are close to the desired capacity CS which is equal to 50. So they fluctuate around the desired capacity. Similarly, in figure B, the total number of active prosumers with wind turbines also fluctuate close to its desired capacity CW. The evolution of the total number of active energy consumers are also fluctuates around the values. You can find the references, the following references. Now we saw the solution to regulate the number of prosumers and consumers in a smart energy community. The solution incurs little communication overhead, as our feedback signals just sends real numbers, theta S, theta W, and theta C. So the communication overhead is very low, and moreover, the prosumers and consumers, they do not need to share any information, so there is no communication among the prosumers and consumers. We saw that the average number of time prosumers and consumers were active reaches to optimal value over time. One of the future work could be, and it will be very interesting, to prove the convergence and the convergence of the average allocations, and they can be proved using the multi-time scale stochastic approximation techniques. Interested readers can refer the book of Borkar, and they can find it in the references. Citation details are as follows. You can reach out to me and can find the contact details at my web page.